the study of extreme physics, brought us the bomb. It has taken us inside the violent death of a star. And now, it has brought us face to face with the most destructive force in nature, a supermassive black hole. How large, how powerful can these monsters get? And what can they tell us about the extremes of time and space? The year was 1990. Hope for a new age of scientific discovery rose into orbit aboard the Hubble Space Telescope. A technical flaw in its optics, requiring astronauts to fly up to repair it, would delay, but not stop, this new age from dawning. In 1994, astronomers pointed the newly repaired Hubble at one of its most important targets, a giant elliptical galaxy 50 million light-years from Earth called M87. Pushing deep into M87's core, they glimpsed a powerful jet of super-hot gas extending 5,000 light-years into space. With Hubble's remarkable resolving power, astronomers measured the speed of the gas racing around the center. They concluded the gravitational source driving these motions is a black hole, weighing in at 6.6 billion times the mass of our Sun. News of M87 joined a flood of discoveries beaming down from Hubble's instruments. The public was captivated by strange and majestic shapes, captured from mysterious realms far beyond Earth. To scientists, Hubble was part of a quickly expanding arsenal of observing tools. A growing fleet of space observatories scanned the light of distant objects across the entire electromagnetic spectrum. On the ground, a new generation of giant telescopes with precision mirrors and dynamic optics allowed observers to look deep into the universe. Astronomers, used to long nights of painstaking camera exposures, were now awash in data streaming in from distant corners of the cosmos. A new vision of the universe emerged, one defined by vast energy releases, titanic collisions, mysterious new forces, and nature's strangest phenomenon, the black hole. Once thought of as mere curiosities, black holes have taken center stage in our understanding of the universe and how it came to be. A black hole begins its life in the brilliant light of a dying star. Within the folds of our galaxy, the energy let loose by supernovae stirs the celestial mix. Shockwaves from these explosions cause gas to condense, then ignite. Stars are born, sometimes hundreds at a time. Intense stellar winds from these newborn stars sculpt majestic castles of gas, the great nebulae long admired by astronomers. Yet, for the giant stars that set this process in motion, the consequences are grim. Back in the mid-1800s, mariners plied southern seas by the light of a brilliant star just off the plane of the galaxy in the constellation Carina. For over a decade, it was the second brightest star in the sky. Astronomers have been studying it intensively ever since. The star, named Eta Carinae, had undergone what's now known as the Great Eruption, an outburst that expelled two luminous lobes of gas that stretched some 12 trillion kilometers from end to end. Astronomers recently found that Eta Carinae is actually two giant stars closely orbiting one another. To explain the extreme turbulence of this scene, scientists modeled the fierce hot winds roaring out of these two companions. The orbital motions of the two stars allowed them to peg the larger one at 90 times the mass of the Sun. Eta Carinae is a supernova waiting to happen. In time, it will seize with convulsions, then collapse and explode. Throughout history, our understanding of space has been shaped by a handful of supernovae visible to the naked eye. Some archaeologists believe this drawing depicts a supernova spotted by North American stargazers in the year 1054. The same event was also recorded in China, Korea, and the Middle East. In Europe, supernova sightings help dispel the prevailing belief that the heavens are static and unchanging. The astronomer Tycho Brahe saw one in the year 1572. "I was led into such perplexity by the unbelievability of the thing," he wrote, "that I began to doubt the faith of my own eyes." In modern times, astronomers have intensively studied the remnants of the 1054 explosion, the famous Crab Nebula. Waves of radiation roaring out of the explosion have etched circular patterns in the surrounding gas, seen here in radio, infrared, optical, ultraviolet, and X-ray light. You can see signs of a jet shooting out of the central region. This energy is coming from a tiny spinning object in the center, the size of a city. This neutron star is not made of any elements, but subatomic particles packed by gravity into an ultra-dense sphere. Physicists think of it as a single huge atom. It's roughly equivalent to packing Mount Everest into a sugar cube. Yet some dying stars meet a fate that is stranger still. In 1796, Pierre Simon, the Marquis de Laplace, imagined a breed of dark stars, so heavy their gravity prevented any light from escaping. This idea, a head-scratcher, fell out of favor for more than a century. Isaac Newton had described gravity as a force of attraction between two masses. Early in the 20th century, Albert Einstein's equations showed that gravity is actually the distortion of space-time by massive objects. Thus, a planet, or star, or even a galaxy creates a gravitational well that will bend the path of other objects, or even beams of light. As the physicist John Archibald Wheeler later put it, space-time tells matter how to move. Matter tells space-time how to curve. In 1919, the now famous Eddington expeditions set out to test this wild idea during a solar eclipse. Their data showed that the sun's gravity bent the path of starlight, just as Einstein had predicted. But also hiding in Einstein's equations was a very strange prospect that recalled Pierre Simon's speculation. If an object is dense enough, it will bend a beam of light back onto itself, causing that light to disappear. Physicist Karl Schwarzschild, director of the Astrophysical Observatory in Potsdam, Germany, took this idea to its logical conclusion. Working as an artillery lieutenant on the battlefront of World War I, he stole moments to pore over Einstein's new theory. "As you see," he wrote to Einstein, "the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Schwarzschild realized that objects could become so dense, their mass would be packed into an infinitesimal point, a singularity. He calculated that these odd creations must be bounded by a larger spherical region beyond which no light can escape, the so-called event horizon. But how could such objects actually exist? In 1939, Einstein himself wrote a paper that sought to prove that these strange objects were impossible. But just a few months later, physicist J. Robert Oppenheimer and his graduate students published their own paper on the subject. Taking a fresh look at the mathematics of collapsing stars, they show that if the parent star is sufficiently massive, the force of the collapse will literally crush its core down to a point, an infinitely dense, infinitely curved speck of pure gravitational energy. Oppenheimer went off to spearhead the design of the atomic bomb, having laid the foundations of the modern science of black holes. The atomic age brought a whole new focus on the study of extreme physics. The bomb was terrifying proof, as Einstein conjectured, that a small amount of mass could convert to a huge amount of energy. Researchers studied the enormous forces released when atoms are split apart in chain reactions at the heart of atomic and thermonuclear bombs. Using advanced new computers developed to model and forecast these explosions, astrophysicists began probing the mechanisms at work deep inside stars, where lighter elements burn and fuse into heavier ones. They saw how this can eventually lead large stars to collapse and explode. This grim product of star death entered the popular imagination in 1967, when physicist John Wheeler called it a black hole. Astronomers were already at work looking for these monsters. In 1964, a sounding rocket recorded a high-energy X-ray source in the southern constellation of Cygnus. Later satellites recorded a pulsing rhythm in its light, punctuated by outlandish bursts of energy. After pinpointing its exact location, ground-based observatories detected a giant star that could not by itself emit X-rays. Astronomers deduced that Cygnus X1 is a star with an unseen companion, one that is eating it alive. Enveloped in a halo of glowing gas streaming in from the star, that partner weighs in at 15 times the mass of our Sun. The first confirmed black hole. This computer simulation shows how a black hole makes its presence known. Matter spiraling into the abyss forms what's called an accretion disk. The spinning motion generates powerful magnetic fields that whip up a hurricane of particles and propel them from the poles at nearly the speed of light. If you were to fall into a star-sized black hole, the pull of its gravity rises so sharply you'd be stretched out until just your atoms remained, what physicist Stephen Hawking once called spaghettification. Stellar evolution models suggest there could be as many as 1 billion black holes in our Milky Way alone. Yet, they are dwarfed by a far larger and far more powerful presence, lurking in the very core of the galaxy. The first hints of this presence came in 1932. The Bell Telephone Company was concerned about static interfering with what it saw as a revolutionary new technology: long-distance radio communications. The company tasked the radio astronomer Carl Jansky with finding the sources. Using this ungainly radio receiver, Jansky methodically scanned the airwaves. He traced most of the static to thunderstorms, some nearby and others far away. Then, on September 16, 1932, he picked up a rumble that he could not explain. This particular noise appeared when the antenna was pointed at the constellation Sagittarius, toward the center of the galaxy. It returned every 23 hours and 56 minutes, exactly 1 Earth day in relation to the stars. Word of Jansky's findings got out. He assured the public it was not aliens seeking contact. But it would take another 30 years for astronomers to find out what it was. In the 1960s, advanced radio telescopes began picking up signals from distant space. Not knowing just what they were, observers called them quasi-stellar radio sources, quasars for short. These bright bluish beacons emitted far greater energy than a star. What cosmic engine was driving them? Radio astronomers found that some featured brilliant extensions originating in the centers of galaxies and reaching millions of light years into space. Looking at their light spectra, researchers realized that these were actually jets of superhot gas speeding away at hundreds of thousands of kilometers each second. Could such a feature finally explain Jansky's findings? It would take a new generation of giant telescopes to reveal the answer. Just as the Hubble Space Telescope began its sensational run, several new observatories were christened on the mountains in Hawaii in the north and the Andes Mountains in the south. Two rival teams of astronomers each zeroed in on the galactic center to see what was there. These teams each undertook a multi-decade effort to track a population of stars that seemed to orbit a concentrated source of energetic emission, called Sagittarius A star. Finally, in the spring of 2002, a star labeled S2 swooped in close, accelerating to a remarkable 18 million kilometers per hour. If its path near Sagittarius A star proved erratic, astronomers would know the galactic center was packed with multiple massive objects. Instead, its path was smooth. They concluded that S2 and its companions must be orbiting a single object, weighing several million times the mass of our Sun. A supermassive black hole. This effort, more than 2.5 decades after it began, was recognized with the Nobel Prize in Physics. Since that discovery, astrophysicists have been feeding additional observation data into their supercomputers to better understand how clouds of gas flow around and into the monster, and how its immense gravity drives the motions of stars at the center of our galaxy. The star S2 will inevitably return to the black hole. The pull of gravity will cause its orbit to shrink, pulling it ever closer. Astronomers recently caught a glimpse of what would then happen. A survey telescope in the Andes Mountains recorded the sudden brightening of a galaxy in distant space. Astronomers at the European Southern Observatory turned their telescopes toward the source. The light had come from a galaxy 215 million light-years away. Astronomers tracked the event through to its ultimate demise 6 months later. They deduced that a star had wandered a little too close to a supermassive black hole. The giant began to tear it apart, turning the star into a river of hot gas, fueling a high-energy jet bright enough to be detected from Earth. Astronomers have long nurtured the hope of seeing a black hole directly, to understand its properties and how it disrupts the space around it. In recent years, an international group of astronomers has been working on just such an audacious goal. Like the Eddington expeditions a century before, these scientists hope to test Einstein's theories, only this time in the most extreme laboratory the universe has to offer: a black hole. The idea was to adapt a technique developed over 60 years ago called long baseline interferometry. By synchronizing radio telescopes all around our planet, a team of 400 scientists and engineers created a much larger virtual telescope with an aperture the diameter of Earth itself. It has a resolution equivalent to being able to read a newspaper in Paris while sitting in New York. They call it the Event Horizon Telescope. Their goal: to capture the first ever image of a black hole. Their target: the monster at the center of M87. Probing deep into M87's luminous core, the astronomers struck a delicate balance between filtering out interstellar dust and finding the outlines of their quarry. At a radio wavelength of about 1 millimeter, all the dust and gas obscuring the monster faded away, leaving this ghostly silhouette: a black hole, an object that cannot, by its very nature, be seen. The Event Horizon Telescope relies on a tool that has transformed the study of the universe. To make sense of the vast amount of data captured by the many receivers, researchers developed a series of computer simulations visualizing the complexity of the scene. Here are some of the results. The dark nucleus is the event horizon, a shadow left when the object's immense gravity slows all light to a stop. The singularity, the black hole itself, is hiding in the shadows. The visible ring marks the spinning accretion disk. It's brighter on one side because the gas there is spiraling towards the telescope, its photons piling up. the light from material moving away becomes dimmer as its wavelength stretches toward the red part of the electromagnetic spectrum. From a slightly more distant perspective, you can see how a portion of the inflowing matter is flung out in a fiery, pulsating jet. M87 is a black hole of truly cosmic proportions. It has been bulking up for billions of years on a steady diet of gas, dust, planets, and stars. But it's not the only billion solar mass black hole out there, or even the largest. The Coma Cluster is a dense grouping of galaxies 321 million light-years from Earth. Its center is occupied by a colossal elliptical galaxy cataloged as NGC 4889. It harbors a black hole estimated to be 21 billion times the mass of the Sun. J2157 is even larger. At 34 billion times the mass of the Sun, this ultramassive black hole is 8,000 times larger than the one at our Milky Way's core. The largest black hole yet spotted, TON 618, may weigh as much as 66 billion of our suns. It drives a superluminous quasar shining 140 trillion times brighter than our star. Theoretically, there is no limit to how large a black hole can grow. All it takes is time and the right circumstances. The building boom of ever larger telescope mirrors has given astronomers a whole new vantage point on the life cycle of ultramassive black holes. Here, in the high northern deserts of Chile, they have been combing the early universe for dim clues of black holes on the rise. Out in the southern constellation of Leo, they spotted the most distant quasar yet observed, just 770 million years after the Big Bang. The red dot is light energized by a black hole estimated at 2 billion times the mass of the Sun. How did it form? And what impact will it have on its surroundings? To find out, scientists have launched a major international effort to simulate the early evolution of the universe. The action starts a few million years after the Big Bang. Gravity begins to draw hydrogen gas into large halos, and from there into concentrations dense enough for stars to form. As some stars die, they give rise to black holes. These primordial monsters feed on inrushing gas, growing ever larger while blasting their environments with fierce winds and jets. The scene shifts to visible light as the universe reaches its halfway point. Two galaxies are beginning to form, each with a central region densely packed with stars. Gravity begins to draw the two into a cosmic embrace. The black holes at their centers will inevitably meet and merge. The end result, a galaxy similar to our own, with a supermassive black hole hidden deep in its core. We now move to a much larger scale. The action starts 500 million years after the Big Bang. Matter coalesces in a spiderweb pattern of filaments and dense knots. Amid the formation of countless stars, several larger galaxies develop. As they merge, so do the black holes in their cores. A still larger view tracks the impact these supermassive black holes have on the surrounding universe. You can see bubbles rising quickly from the largest galaxies. These are waves of super hot gas pushed out by winds and jets powered by growing black holes. Such outbursts seed the universe with elements generated by large stars and supernovae. Elements that would one day come together in stars and planets like our own. By pushing outward huge volumes of gas, these hot bubbles slow the growth of their host galaxies, while promoting the formation of smaller galaxies, like our Milky Way. Quasars and the black hole jets powering them are among the most energetic phenomenon known. This one, spotted by the Hubble Space Telescope in the early universe, emits light 600 trillion times brighter than our Sun. And yet, that hardly begins to describe the power unleashed when two supermassive black holes collide. To find out what that will look like from Earth, scientists have simulated the moment just before two supermassive black holes merge. Magnetic and gravitational forces heat up the gas. The pair is enveloped in ultraviolet light. Superhot plasma flowing around and into the black holes glows in X-ray light. The intense gravity of the pair distorts and bends space-time, creating a lens. Albert Einstein hinted that the energy of such a collision goes far beyond the emission of high-energy light. His equations predicted that when massive bodies, like black holes, accelerate or whip around each other, they would disturb the normally smooth fabric of space-time. A series of powerful gravitational waves would move outward, like ripples on a pond. By the time these waves travel the breadth of the universe to reach us, their energy will have nearly dissipated. And yet, scientists believe they have detected them. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they have assembled precision high-powered lasers and some of the most perfect large-scale vacuum chambers ever created. The idea is that as a gravitational wave passes, it will stretch and squeeze the distance between mirrors placed at the ends of 4-kilometer-long tubes. This distortion of space-time, measured by lasers, is incredibly subtle, 1,000 times smaller than the nucleus of an atom. This ambitious undertaking, decades in the making, finally bore fruit in 2015. The instruments at LIGO and its European counterpart each recorded a signal consistent with the merger of two black holes of 29 and 36 solar masses. Scientists calculate that the collision converted the mass of up to 3 suns to pure energy in the form of gravitational waves. LIGO's founders would win the Nobel Prize for Physics in 2017. This simulation shows the pattern of gravitational waves that the pair would have emitted in the final moments of the merger, and just after. As the objects spiral together, the energy carried by each successive wave rises, for the briefest of moments, to 100 billion trillion times the power of our Sun. Collisions like this are extremely rare, but the universe is very large. As their sensitivity improves, LIGO and similar instruments will detect more and more such reverberations in space-time. Remarkably, even this does not begin to describe the power held within a black hole. Imagine a spaceship in the distant future on a rendezvous with a supermassive black hole. Because of the object's immense size, the stretching force is small, allowing the ship to survive as it falls through the event horizon. But not for long. As the ship spirals down, it hits a wall of energy, what scientists describe as the inner horizon. At a black hole's event horizon, matter accelerates to the speed of light. It is then whipped around so fast that some of it gets flung back out and into a collision with inflowing matter. At the inner horizon, the energy rises so sharply, it may well reach nature's limit, equivalent perhaps to the Big Bang itself. Fortunately for us, gravity walls off such extremes behind the event horizon of black holes. Wait long enough, trillions upon trillions of years, to a time when theory says all matter and energy will likely fall inside black holes. Gravity may well draw the entire universe inside a single ultimate black hole. Some theories suggest that it could erupt in a flurry of matter and antimatter, in gases that cool and coalesce into stars, explosions that give rise to black holes, galaxies that envelop and nurture them, while giving birth to solar systems like ours. And so here we sit, on a planet that is an infinitesimally small byproduct of the universe at large. Our imaginations, though, are unbounded as we contemplate the strange and powerful forces that have shaped all we see.